So here's the molecule H2, hydrogen. You've probably drawn its dot structure like this before, which is fine. That indicates that two hydrogen atoms are sharing 2 electrons in a covalent bond. It actually gets more complicated than that, and that's what's going to blow your mind next time. But for now, a simple way that we organic chemists represent this molecule, instead of drawing the 2 dots, we will draw a straight line between 2 atoms, and you need to understand that that line means 2 electrons in a bond. A single bond we're generally going to give the name sigma, not because it's so awesome, though I really don't understand that. Somebody's going to have to explain that to me at some point. Generally, a single bond we're going to call a sigma bond, and we'll use the Greek letter sigma to represent that. When you see the straight line, that just means 2 electrons shared in a covalent single bond. Let's do a related molecule, CH4 or methane. You may have done the dot structure for methane before, showing that each of the hydrogens is sharing 2 electrons with carbon, and carbon is surrounded by 8 electrons, keeping the octet rule. And if we're to apply what I just told you for how organic chemists draw Lewis structures, you could also represent methane like this. However, there is a problem with the way I've drawn it, and the problem is that the way I've drawn it has an unrealistic shape. In the sense that if you look at that and interpret it literally, you're like, is methane flat and are all the bond angles 90 degrees? And the answer is no. You know, because of valence shell electron pair repulsion theory, which you guys probably pronounced Vesper because it sounds better than Vesper. But whatever that is, you know that the shape of methane should be what? Tetrahedral, a molecule surrounded by 4 things. Those 4 things are going to, by electron repulsion, try to get as far apart as possible. An atom surrounded by 4 things. So we need a way to demonstrate the tetrahedral shape of methane. How are we going to do that? Well, we're going to introduce a new convention. Whenever we draw a straight line, we're going to indicate that that straight line, or it is assumed that that line is portrayed in the plane of the page. And then we're going to use other types of lines to indicate shape. So we will use a wedge to indicate that this hydrogen is angled down towards the left, but pointing out at you. And that this hydrogen with a dash is angled down towards the left, but pointing away from you, such that if you could rotate this molecule around and examine it from all possible angles, you would see that all of the bond angles are about 109 degrees. Some of you know that that's 109.5, which is good for you, but we don't need that many significant figures, or really any significant figures in this class. So. All right, let's give you a picture of what that molecule actually looks like so you can see the analogy between what we've drawn and what the molecule looks like. Here is an app called Spartan that shows 3-dimensional structures of molecules. This is methane, and you can see the tetrahedral shape with the 109-degree bond angles. If I align this molecule so that the 2 bonds, so that one bond is pointing straight up in the plane of the page, and the other bond is angled down towards the right in the plane of the page, you can see that on the other side, you've got a hydrogen that's angled down to the left, pointing out at you, and then a hydrogen that's angled down to the left, pointing away from you. And you can see that it's kind of it would be kind of difficult to draw that molecule like this because the hydrogen in the front sort of overlaps the hydrogen in the back. And so we try to draw that like this. Okay? A question that came during the first hour was, does it matter which way the dashes and wedges are pointing? Yes, it does. In order to portray tetrahedral shape, pay attention to the straight lines. They form an arrow, and that arrow points in the direction that the dash and the wedge must be. It's totally fine to draw the molecule like this. It would be totally not fine to draw the molecule like this. You see how that's unrealistic and doesn't actually capture the shape? We're going to put the big X's through that one to indicate don't draw it that way. Yes?
What if we just switch the wedge and the dash?
Yeah, so you can switch the wedge and the dash. One's up, one's on top, one's on the bottom, one's to the left, one's to the right. That doesn't matter. Okay. So let's now use what we know to draw a couple of more interesting molecules. Let's do CH3, CH2, CH3. And we'll draw each of the carbons bonded to other carbons. And then the carbons on the end have 3 bonds to hydrogen. One is a dash, one is a wedge. Same thing here. And then same thing here. Okay? This molecule is called propane. You've been to the gas station to buy it so you can grill your delicious meats of various kinds. Or maybe you guys are into smoking delicious meats. I'm not sure. But all right. So as molecules get bigger, drawing them starts to become very exhausting, and we are lazy as organic chemists. So we've developed a shorthand for drawing molecules that allows you to save time, but it only works if you understand the rules. So here is the shorthand, what is called skeletal structure for propane. I am done. Okay, so you'll notice that we're not drawing where the carbons are. It is assumed that there is a carbon every place a line ends or intersects another line. So there's a carbon, there's one there at the vertex, and there's another carbon. You have to know that. That's the shorthand. Second, you also don't draw the hydrogens. You can, but it's optional. And it is assumed that every carbon has a sufficient number of hydrogens to give it a full octet. So when I look at this one, I notice that carbon is bonded to one other carbon. So to have a full octet, that carbon must also be bonded to how many other hydrogens? 3, right? Okay, same thing here, that's a CH2. Okay, so you need to get used to seeing in your mind or knowing that the hydrogens that are implied but not shown are there, okay? One important rule for skeletal structures is if you write the letter C out instead of using the easy way of not writing the C, you must draw the H's on that carbon. So what I've drawn here is not okay. What I've drawn here is totally okay. If you write out the C, you must write out the H's. Yes?
So in that second case, you only have to write out the H's for the C.
For the C that you drew. Yep, you only have to draw out the H's for the C that you drew. Yes?
Is there a name for this, like the typing of structure that we did before that shows all the H's?
We would call that a Lewis structure. And honestly, I'm going to forget to call that a skeletal structure. I'm just going to call it a Lewis structure or just a structure. Yeah. Okay, see anybody else? Yeah.
Would you only write out the C's if you were like missing an electron or something like that?
So would you write out the C's if you were like missing an electron? We're going to deal with what happens when we have not enough electrons or too many electrons. That's called formal charge. And yeah, in cases like that, you might. It would depend. But I'll give you some cases like that. All right. Let's talk about... Nope, actually what we're going to do is I want to test your ability to draw the hydrogens that are implied but not shown. I'm going to draw this lovely hexagon. That is a molecule called cyclohexane. Now you have approximately 30 seconds to draw out the full structure with all the C's and the H's that are implied but not shown. Ready, set, go. Okay, you good? Need more time? Drawing frantically. Okay, take just maybe 20 seconds to compare with a friend. Or to meet a new friend. Yes, come on down. Yeah, wedges, dashes, draw the whole thing. Your name is?
Haley.
Haley, all right, thank you, Haley. Now, my job is to heckle if I don't like it. I'm just kidding. We're not. I used to be a primary chorister, and the kids in the back, including my son, are always heckling me.
Are all the wedges supposed to be on the outside?
Yes.
Okay.
Yeah, so pay attention to the direction of the two bonds that are straight lines in the plane of the page. Those will point in the direction you're supposed to put the wedges and the dashes. Nice. And now you're seeing why we don't do this, because you can draw a hexagon in about 5 seconds, maybe less. All right, let's see, dashes 2 should also be pointing outward.
Oh,
Yep, that's great.
do you want me to do that?
Yeah, go ahead. And if you want, the eraser's right there.
That'd be too easy. Okay.
There you go. Right, so note, and this is something that's easy to mess up, and I see sometimes on exams or problem sets when people are drawing things, is drawing the wedges and dashes in the wrong direction. It looks like it doesn't matter now, but when you learn about something called stereochemistry, it actually matters a whole lot. But the most important thing now is that it correctly, thank you, let's give Haley a hand. Thank you. Very good. So, wedge, dash, and remember, you know which way they point you know which way to orient them by looking at the two lines that are in the plane of the page. Okay, another rule for skeletal structures is you must actually draw heteroatoms. We'll tell you what that means in just a second. And if they have any, they're hydrogens. So a heteroatom is anything not carbon or hydrogen. Organic molecules have a lot of carbon and hydrogen. That's why they're the ones we abbreviate. The other atoms, including nitrogen, oxygen, fluorine, chlorine, sulfur, phosphorus, etc., we actually have to draw out. And if there are any hydrogens, we have to draw those too. So here is a molecule which you read in section 89 of the Doctrine and Covenants we are not supposed to imbibe. It is called ethanol. And its skeletal structure you can draw like this, and that's okay. You could also draw it like this, and that's okay. But what is not okay is to draw it like that. Okay? If there's a hydrogen attached to a heteroatom, now that's going to be confusing to you because I just crossed out the not okay. So we got a double negative there, aren't we? All right. There we go. That's better. So it's not okay, it's just not okay. You have to draw the hydrogens that are present on heteroatoms, always. Okay, now we need to deal with molecules that are not neutral. And most of you are familiar with something called hydronium, which you've drawn as H3O+. And you maybe are even used to drawing it like this, maybe to give a more realistic representation of its shape, which should be something trigonal pyramidal with a lone pair here. One of the hydrogens is a wedge, the other is a dash. And you may have even seen people put brackets on it and put a positive charge outside the bracket to indicate that the whole molecule is positively charged. But in organic chemistry, we use something called formal charge to help us keep track of the electrons in the molecule. Formal charge is basically a bookkeeping of electrons. It's a way to count the electrons in a molecule. And it's a way to tell really quickly whether a molecule is charged or not. Now, of course, if you wanted to tell whether a molecule is charged or not, like hydronium, you could count up all the protons in all the nuclei, and then you could count up all the electrons, not only those involved in bonds or lone pairs, but also the inner shell electrons, and compare the two, and you'd come up with the right answer. That's kind of tedious, so we have a shorthand way of doing it that always gets you the right answer if you follow the procedure. And that process is called formal charge. Now, why is it called formal? Not because the charge is wearing a tuxedo, but because it doesn't actually represent distribution of electrons in a molecule. So formal charge may not, doesn't necessarily actually represent distribution of electron density in the molecule. And I'll show you what that means in a moment. But to assign formal charge to an atom, you follow the following procedure. So let's take this Lewis structure of hydronium, and I'm going to assign formal charge to the oxygen by asking the following question. First, how many valence electrons does the atom usually have? In the case of oxygen, you look at the periodic table and you see its column number. Oxygen's in the 6th column, has 6 valence electrons normally, okay? And then you're going to compare that number with how many electrons it owns, where the number of electrons that it owns equals all of the electrons in lone pairs and half of the electrons in bonds. So for this oxygen, if we zoom in on it, how many electrons does that oxygen own? There's 1 lone pair, so 2, and then there's 3 bonds. Each bond represents 2 electrons, so half of the electrons in bonds, 1, 2, 3, 4, 5. So we would say that oxygen owns 5 valence electrons, and therefore it has a +1 formal charge. And we will indicate that by drawing a plus right next to the oxygen. Okay? Now, we can look at the hydrogens and assign their formal charge. This hydrogen owns how many electrons? Just 1. 2 in the bond, but it only owns half of those, right? So 1 electron. It normally has 1 electron for 1 valence electron, so overall formal charge is 0. 0 formal charges, you don't need to indicate with a 0, you just don't draw anything next to it. But all non-zero formal charges you must draw in order for the structure to be correct. Yeah?
Do you want us to draw it on every single atom, or do you want us to draw it on the central atom?
Do I want you to draw the formal charge on just the central atom or every single atom? It's not about central or peripheral, it's about all non-zero charges must be drawn. All non-zero formal charges must be indicated. So the reason we're not indicating them on the hydrogens is not because they're peripheral, but because their formal charge is 0. Yep. Okay, so let's practice. There's a whole bunch of molecules that we could draw that have non-zero formal charges. Let's see where to begin. Why not? Okay. What is the formal charge on that oxygen? Oxygen normally has 6 valence electrons. How many does it own currently? 7. 6 from the lone pairs and 1 from the sigma bond. Therefore, the formal charge on oxygen is -1. We'll indicate that with a negative. Do I need any formal charges on any of the other atoms that are implied but not originally shown in this molecule? Nope. The hydrogens have a 0 formal charge. What about the carbons? Carbon normally has 4 valence electrons, currently owns 4, 0. Okay, 0 formal charge, no need to draw it. Okay, now I said earlier that formal charge is simply about electron bookkeeping. It lets you know that the molecule we've just drawn is negatively charged. I told you, though, that it doesn't necessarily actually represent distribution of electron density. Sometimes it will, sometimes it won't, and you have to use other knowledge to figure that out. We're going to talk about that a little bit later in the class, but let me just illustrate that point real quickly now in showing you that oxygen is more electronegative than hydrogen, right? So you would predict that even though oxygen has the positive formal charge, most of that actual positive charge is felt on the less electronegative hydrogens. So we would know about hydronium that it's actually the hydrogens that have partial positive charge on them. We will indicate that partial positive charge with a Greek lowercase letter delta and then the plus sign to indicate partial positive charge. Now, you don't have to draw partial positive charges. In fact, most of the time we won't unless I'm highlighting it for you to demonstrate something you should know, but you have to use your electronegativity intuition to help understand the actual distribution of electron density. If you want to know which part of the hydronium molecule is electron poor, it's the hydrogens, not the oxygen, even though the oxygen has the plus formal charge. Does that make sense? So that's why it's formal and not actual charge. However, sometimes things will line up. This oxygen is negatively charged, and you know that oxygen's more electronegative than carbon, so it is correct to say that this oxygen is electron rich and would have negative charge on it. So, as to the actual distribution of electron density in the molecule, you have to use your electronegativity intuition. Formal charge is just about keeping track and making sure the structure is correct. Okay, we don't have a huge amount of time. I want to talk about something else in our last few minutes, but I'll just give you a couple of additional examples. This nitrogen bonded to 4 things has a positive formal charge. This boron bonded to 3 things has a 0 formal charge. This boron bonded to 4 things has a negative formal charge. And then this nitrogen in this strange molecule that I've just drawn here should have a 0 formal charge. And you'll have chances in the study guide to practice this, but you should also do these examples and convince yourself you can get the right answers. There are definitely going to be problems on your first exam where I point an arrow to an atom in a structure and you multiple choice have to choose the right formal charge. And so make sure you get that, all right? Okay, in the last little bit, I want to talk about something that's called resonance, which you've heard about, but I can basically guarantee you don't understand well enough for this class. So we're going to revisit it multiple times and give you a really deep dive into what resonance means. But for today, resonance is when you have 2 or more ways of arranging the electrons in a Lewis structure. And usually, getting from one of these arrangements to another involves moving. I'm putting the moving in quotation marks because you will see that the electrons are not actually moving. They're just spread out in space. But for today, we move usually lone pairs and electrons in pi bonds. What do I mean by pi bond? Well, you probably heard of a double bond. I'm going to draw this molecule here. Before we get to that issue of pi bond, what should the formal charge on this oxygen be? -1. Good. How about the formal charge on that one? 0. So notice that this oxygen has 2 bonds to carbon. You've probably learned that that is a double bond. And you probably learned that, oh, that oxygen is sharing 4 electrons with carbon instead of just 2. All of that's true, but it's more complicated than that. We will call the first bond of a double bond a sigma bond. And it doesn't matter left or right. You can't actually tell in this drawing. You just need to know that one of them is a sigma bond and one of them is a pi bond. And they are different from each other. They come from different overlap of orbitals, which you're going to learn about next time, and it's going to blow your mind. So going from one resonance structure to another is going to involve moving around lone pairs and pi bonds. Generally, for our purposes, we're not going to change the sigma bonds, and also we're not going to move atoms. All right? Yes?
When we do the skeletal structure, are we encouraged to do the lone pairs like B1?
So when you draw a skeletal structure, do you have to do the lone pairs? No. At the beginning when you're learning formal charge, is it useful? Yes. Okay. So I can draw an alternative resonance structure, and I'm going to use this double-headed arrow here to indicate that the 2 structures I'm drawing are resonance structures of each other. And you're going to see that I'm switching where a pi bond is, and I'm switching which oxygen is negatively charged. Now, I haven't moved atoms, and we're not talking about flipping the molecule and slapping it over. We're saying that if you kept all of the atoms in the same place, what's on the right is just as valid a structure as what's on the left. To get from the resonance structure on the left to the one on the right, I can use what are called curved arrows to keep track of what's changing. I will take one of the lone pairs on the negatively charged oxygen on the left, and I will draw an arrow that points to the space between the oxygen and the adjacent carbon. That indicates that I'm taking those lone pairs and I'm moving them to form a pi bond with the adjacent carbon. Now, if I stopped there and didn't do anything else, the carbon in the middle would now have 5 bonds. That's more than an octet, and that breaks a Lewis structure rule. No more than 4 bonds or 8 electrons around a second row element. So in order to not break the octet rule, I must break the pi bond and move it out to be a lone pair on the adjacent atom. So that's where that lone pair comes from. Okay? That's how I convert one resonance structure to another, using that 2-step of arrows. Now we need to talk about what that means, because right now you're probably thinking, oh, I get it. The electron, the negative charge hops from the one oxygen to the other, and half the time it's on the one oxygen, half the time it's on the other. That is simple and a great image, and it is exactly wrong. The negative charge is simultaneously in 2 places at the same time. And that's the mind-blowing thing, and we're going to talk about how that can be. In the meantime, I want you to practice converting one resonance structure to another with the molecule that I'm going to draw for you, and I want you to do this as an exercise before you come to class next time. I want you to use this same sequence of 2 arrows to convert the structure on the left to the unknown resonance structure on the right. Okay? That's all we have time for today, so stay tuned for Learning Suite to go live and the study guide and syllabus and problem set to be available. See you next time.